Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we are going to discuss entropy and the second law of thermodynamics. So I write, let me this color, entropy and the second law of thermodynamics. This is our topic today. Remember, in the last lecture or lectures, we discussed entropy for reversible and irreversible processes. Remember, first we defined a change in entropy SF minus Si as dQ by d I to F. This way we defined the change in entropy between any two states I and F. But we said this is valid for a reversible process, right? Then we solved a problem in which I state the problem in order to remind you. Problem was like this: a lump of ice whose mass was given was 235 grams that was melting reversibly to water. Temperature was constant 0 degrees Celsius throughout the process, and we calculated the entropy change for the ice and for the reservoir also. So we saw for that process the change in entropy of the ice plus reservoir taken together was 0. Then we said this is true for any reversible process, right? Then we discussed the entropy for irreversible processes, where we said how can we find the entropy change for an irreversible path. So we exploited the fact that entropy is a state function. So to find the entropy change for an irreversible path between two equilibrium states, what we do, we find a reversible process connecting the same states and calculate entropy change for that reversible process using this same equation. We did an example for irreversible process also. Irreversible heat transfer were discussed, where we took two blocks at different temperatures initially, right? Then we brought them in contact with each other until an equilibrium temperature was attained. This process is irreversible. So we found a reversible path connecting initial and final state and calculated the entropy change and showed that this entropy change of the total system plus environment for this irreversible heat transfer is positive. That means entropy of the system plus environment increases. Now we come to the second law. The second law, in its most general form, in terms of entropy, is expressed as, I write, The second law of thermodynamics, in its most general form, second law of thermodynamics in its most general form is expressed in terms of entropy as I write a statement, this color, in any thermodynamic process that proceeds from one equilibrium state to another, the entropy of the system plus environment either remains unchanged or increases. I repeat, in any thermodynamic process that proceeds from one equilibrium state to another, the entropy of the system plus environment either remains unchanged or increases. This is the statement of second law of thermodynamics in terms of the state function entropy. For reversible processes, the entropy remains unchanged. As we discussed already, you must remember when we say the entropy remains unchanged, for reversible process, you have to take into consideration the entropy of the system plus environment, right? Likewise, for irreversible processes, that is for all natural processes, because all natural processes are irreversible in nature, the total entropy of system plus environment must increase. It is possible that the entropy of the system might decrease, but the entropy of the environment always shows an increase of greater magnitude, so that the total change in entropy is always positive. You must remember, no natural process, no natural because natural process is irreversible. No natural process can ever show a decrease in the total entropy of system plus environment. You must remember this. No natural process can ever show a decrease in the total entropy of system plus environment. Sometimes for environment, we use the word surroundings. And for system plus environment or system plus surroundings, we use the word universe. Right? Now, as was the case for the zeroth and first laws, implicit in this form of the second law is a statement about the existence and usefulness of a new thermodynamic variable, in this case, the entropy. You must remember the second law, like the zeroth and first laws, is a generalization from experience. It cannot be proved. Cannot be proved, but can be tested in a variety of circumstances. We can test it. We can show that it is consistent with observation and that it forbids processes that might seem to satisfy all other known laws, but that are not observed. Now let us take other two statements of second law which we have already discussed and compare them or see they are consistent with this type of statement, which is in terms of entropy. First, I take Kelvin Planck's statement of the second law. Kelvin Planck statement of the second law. What is Kelvin Planck's statement of the second law? In simple terms, it says that we cannot have a perfect heat engine. We cannot have a perfect heat engine. Remember the schematic of the heat engine was like this. We have already discussed it. So all heat engines can be represented by this diagram. So we have hot reservoir at temperature TH. We have cold reservoir at temperature TC, right? Now, if this is engine, what engine does, it takes heat from hot reservoir, rejects some heat to the cold reservoir, and in the process, it does some work. So it takes some heat, rejects some heat, and does some work for us, right? So remember, we represented heat taken by the engine from the hot reservoir as QH, and we represented heat rejected to the cold reservoir by QC mod, because we're taking only the absolute value, because our sign convention is heat rejected is negative. And work done was W, right? Then we said perfect heat engine means it rejects no heat. For a perfect heat engine, QC, heat rejected, is 0. That means it takes some heat from the hot reservoir and does equal amount of work. And remember, our engine is working in a cycle, right? So we want to justify now why we can't have a perfect heat engine in the light of this statement of second law, which is in terms of entropy, right? I repeat, we want to see why we cannot have a perfect heat engine in the light of second law of thermodynamics statement in terms of entropy. That means this statement, right? Let us explain it. See, all engines operate in cycles. All engines operate in cycles. What does that mean? That means because entropy is a state function, right? So in any cyclic process, change in entropy is 0. Now, since all engines operate in cycles, the entropy change, the entropy change for the system, the entropy change for the system is what? The working substance of the engine. That is, the working substance must be 0, right? For one complete cycle of operation. For one complete cycle of operation, right? The entropy change for the system, that is the working substance, must be 0 for one complete cycle of operation. Remember these quantities: heat rejected, heat absorbed, and work done are for one cycle, right? Now, second law of thermodynamics says in terms of entropy that entropy of the system plus environment either remains unchanged or increases. There are only two possibilities. Either it will, this change in entropy of system plus environment either remains unchanged, that means it must be 0, or it must increase. It cannot decrease, right? Now see, Kelvin Planck's statement says we cannot have a perfect heat engine. We will justify why we cannot have, because it will contradict this particular statement, right? See how. So our engines are operating in cycles. The entropy change for the system working substance must be 0 for one complete cycle of operation. Now, in a perfect engine, the environment means what? Our environment is heat reservoirs. Now, in perfect heat engine, our working substance takes heat from hot reservoir. It loses no heat. It takes heat from the environment. Hot reservoir is environment. So in a perfect engine, the environment releases heat, Q, at temperature T. What is this Q? It is heat taken from the hot reservoir. This T is temperature of the hot reservoir. I'm writing now in general T and Q. Now, since environment releases this much heat to the working substance at temperature T, that is the temperature of the hot reservoir, which is our environment. Therefore, the entropy change for the environment, entropy change for the environment is what? Is minus Q by T, a negative quantity. Because heat released is taken as negative. So heat is taken from the hot reservoir. Hot reservoir is our environment. So it releases heat to the working substance, right? Working substance operates in cycle. Its change in entropy is zero. The system entropy is zero. His system's change in entropy is zero, but the change in entropy for the environment is minus Q by T, right? Therefore, the total change, in entropy, total change in entropy of system plus environment. System plus environment is a negative quantity, is a negative quantity in a perfect, is a negative value in a perfect engine, which contradicts this statement. It says entropy of the system plus environment either remains unchanged or increase. That means either the change in entropy is zero or is increases, means this change is positive, greater than zero. It cannot be negative. That means it decreases, right? Now, since for a perfect engine, the total change in entropy of system plus environment is negative for a perfect engine, so existence of a perfect engine would violate the entropy statement of the second law, so it cannot exist, right? Now let us justify the Clausius statement of the second law. The Clausius statement of the second law of thermodynamics. You remember it, it is in terms of refrigerator, and in simple terms it says we cannot have a perfect refrigerator, right? Now, what is the schematic of a refrigerator? So we have hot reservoir at temperature T, C, TH. We have cold reservoir at temperature TC. Then if this is our refrigerator, there is a refrigerator. What it does, it takes heat from cold reservoir and rejects heat to the hot reservoir, and in the process we have to do work on it, right? Now, what is perfect refrigerator? For a perfect refrigerator, we don't need to do any work. W is 0. W is what? Work done on the working substance. So we don't need to do any work on it. That means we can run our refrigerator without electricity, right? This is the schematic. So it takes heat and it rejects equal amount of heat if it is perfect. And remember, we are talking of refrigerators working in a cycle. Now let us see why we cannot have a perfect refrigerator. Now in a perfect refrigerator, again the system has no entropy change in a complete cycle. Why? Because it works in a cycle. Since it works in a cycle, I change the color. Since it works in a cycle, so in a perfect refrigerator, the system has no entropy change. The system has no entropy change, right? That means change in entropy of the system is 0 in a complete cycle. But the environment releases heat. Here it releases. Cold reservoir releases heat and hot reservoir takes heat. Now hot reservoir plus cold reservoir overall is environment. That means environment releases minus Q amount of heat at the temperature of cold reservoir and absorbs Q amount of heat at the temperature of hot reservoir. Here it absorbs, here it releases. Released heat is negative and absorbed heat is positive. So my environment, hot reservoir plus cold reservoir, is, if it is perfect, we are talking a perfect refrigerator because we are seeing work is 0. So my environment releases heat minus Q at Tc and absorbs same amount of heat Q at the temperature of hot reservoir. So the total change in entropy of the environment, total change, this is not just total change of the system plus it is environment. I write environment here. So total change in environment, total change in entropy of the environment is Q by TH minus Q by TC. Because this much heat is released, this much heat is absorbed. I take Q common, I get what? 1 by TH minus 1 by TC, right? Now, let me move to the next page. But TH is greater than TC. TH is greater than TC. What does that mean? This change in entropy of the environment is negative. That means delta S environment is negative, because when TH is greater, this term will be smaller, negative term will be bigger, overall change in environment will be negative. Now change in entropy of the environment is negative, but the change in entropy of the system is 0. Therefore, when we add these two changes, the total change in entropy of the system plus environment is negative. For a perfect refrigerator would thus violate entropy statement of the second law. So we cannot have a perfect refrigerator, right? There is another idea here, the arrow of time. It is the change in entropy that ultimately provides us with the answer to why systems will naturally evolve in one direction with time and not the other. Systems always evolve. You must remember, systems always evolve in time, evolve in time in such a way, in such a way that the total entropy of system plus environment increases. I repeat, systems always evolve in time in such a way that the total entropy of system plus environment increases. If you observe a system in which the entropy appears to decrease, you can be sure that somewhere there is a change in the entropy of the environment large enough to make the total change in entropy positive. So this is all for today. Thank you. Assalamu alaikum.